In a furnace running past 1000 degrees, the smallest part often decides whether the whole assembly holds. A metal washer here would soften, oxidize, and let the joint drift. A polymer one would simply char away. The little white ring turning here does neither. It keeps the clamp tight and the current blocked, glowing hot and completely unbothered. First and foremost, it insulates. Where a polymer or mica washer breaks down as it heats, dense alumina holds a dielectric strength near 14 kV per millimeter and a volume resistivity above 10 to the 14th ohm-centimeters. And it keeps that insulation even as the temperature climbs past where organic materials fail. Current that would arc across a softer spacer simply cannot cross it. Insulating is only useful if the joint stays tight. Ground and lapped to a controlled thickness, the washer keeps its dimensions where a metal one would relax, so the preload on a bolted joint stays where it was set. With a compressive strength in the thousands of megapascals, it spreads clamping load across alloy and refractory plates without crushing or creeping, cycle after cycle. The surroundings rarely play fair either. Alumina tolerates acids, alkalis, solvents, and combustion atmospheres that corrode metal hardware, and because the fully dense body is non-porous, it can sit in a vacuum bake-out without outgassing. In clean and high vacuum fixtures, that keeps the assembly stable and uncontaminated. All of that begins with the chemistry. Aluminum and oxygen bond into a dense corundum lattice with their electrons held firmly in place, which is precisely why alumina insulates so well and withstands high voltage without conducting. The same rigid bonding gives it hardness, heat resistance, and dimensional stability in one material. How far it can be pushed depends on purity. Moving from around 96% alumina toward 99% and beyond lifts the strength, the insulation, and the temperature limit, while a clean, fully sintered grain keeps the surface stable in vacuum and aggressive atmospheres. The richer the alumina, the more demanding the joint it can sit in. No two assemblies bolt up the same way, so each washer is cut to the joint. Inner diameters run from about 1 mm up to 40 to clear common screw sizes, outer diameters reach past 50 to spread the load, and thickness spans from thin shims under a millimeter to heavy sections several millimeters deep. The faces are ground to a tolerance near 1/10 of a millimeter. Beyond size, the form follows the hardware. Flat washers for simple stacks, top hat and shouldered shapes that wrap a screw or feed through to insulate it on every side, special thicknesses for a target preload, and bores matched to the fastener. The faces are lapped flat wherever clamping force has to stay even. Nowhere is that combination tested harder than inside a heat treatment or vacuum furnace. There, threaded rods and alloy fixtures clamp parts through cycles that climb past 1600 degrees, and ordinary metal washers soften, oxidize, and lose their grip, letting fixtures shift and loads run uneven. An alumina washer rides through the same heat with its clamp force intact and its insulation unbroken, spreading the load across the plates and standing up to the vacuum without shedding gas. Hundreds of cycles later, the joint is still where it started. Tellingly, the part that asks for the least attention in the furnace is the one quietly keeping everything else in place.